Welcome back to the Global Greek Influence podcast. I'm Panayiotou Pimenidou. If you want to be up to date with the podcast news, subscribe to the Global Greek Influence podcast on Apple Podcasts, Spotify, Google Podcasts, Anchor FM, Amazon Music, and 11 more podcasting platforms. In addition, you can contact the Global Greek Influence through the podcast Facebook and Twitter accounts, the podcast website globalgreekinfluence.com, and the podcast page on LinkedIn. Today, Dr. Eleni Diamanti will discuss the quest of quantum computing and communication. Dr. Eleni Diamanti is a CNRS researcher at Sorbonne University in Paris, France. She received her diploma in electrical and computer engineering from the National Technical University of Athens in Greece in 2000 and her PhD in electrical engineering from Stanford University in the United States in 2006. She then worked as a Marie Curie postdoctoral scholar at the Institute of Optics Graduate School in Palaiseau in France before joining the CNRS in 2009. Her research focuses on experimental quantum cryptography and communication complexity and on the development of photonic resources and of protocols for quantum networks. She is a recipient of a European Research Council starting grant, the Vice Director of the Paris Center for Quantum Computing, part of the European Union Quantum Flagship, the CNRS Researcher Director at the LIP6 Laboratory of Sorbonne University in Paris, a steering committee member of the French Regional and National Networks on Quantum Technologies, and an elected member of the Board of Stakeholders of the European Public-Private Partnership in Photonics. She also serves as Associate Editor for Science Advances and Quantum Science and Technology. She sits on a scientific committee set up by the French Ministry of Higher Education to promote France's role in the Quantum Flagship, a €1 billion 10-year European Union program launched in 2017 to support quantum technology. Welcome to the show, Eleni.
Hello, thank you very much for the invitation. It's a pleasure to be here.
It's my pleasure and honor to have you here with us today. We always see a smooth career path by reading one's CV or public professional activities. Was it clear to you from the beginning you would lead research in quantum computing? How did your journey unfold?
Okay, so that's a difficult question. I guess we cannot know from the very, very beginning exactly what role we're going to play in science. One thing I can say for sure is that during my studies at the National Technical University of Athens, the Polytechnic of Athens, I knew quite quickly that I wanted to be involved in research. In academic research, and my path since then has not diverged from this initial intuition. And so what I did after the studies was to look for a PhD, and so this brought me to the US for my PhD, and then quite naturally I looked for a position in academic research, and then what happened coming back to Europe, and then so as I say, sometimes I haven't had a real job ever, meaning a real job where you're not working in actual research, where in fact you make the advantages that you make your own research planning and set your objectives. This does not mean that we do not work very hard, because exactly actually when we have we set out to materialize these objectives, and especially when you work in a field that has become quite, as you've noticed, and I guess we're going to discuss further about this, quite popular, and we have lots and lots of responsibilities, and this is something I like a lot. So this is definitely so I wouldn't be able to pinpoint exactly at which point I knew it was going to work like this, but it unfolded quite naturally. I actually never diverged quite a bit from this path.
You're set off to an exciting journey because the quantum technologies have become part more and more of our reality and will become more in the future, especially in the next 10 years. A quantum computer harnesses quantum mechanics to fast forward processing power, even outperform today's and tomorrow's supercomputers. Quantum computers use qubits, typically subatomic particles such as electrons or photons. Generating and managing qubits is a scientific and engineering challenge. Companies such as IBM, Google, and Rigetti Computing use superconducting circuits cooled to temperatures colder than deep space. Others, like IonQ, trap individual atoms in electromagnetic fields on silicon chip in ultra-high vacuum chambers. The goal is to isolate the qubits in a controlled quantum state. What could be the near-term benefits of existing quantum technologies without waiting for decades for the arrival of quantum computers?
Okay, so maybe what would be helpful here is to tell the audience that the quantum technologies has been structured during these last few years in four major pillars around which we organize, we set ourselves in our objectives. We talk about applications as well, because your question is about applications. So this is actually quite linked to that. So these four pillars, strategic, but also technological pillars, I would say, an application, and it also makes sense from an application sector point of view, are quantum computing, which has been the focus of your question, so which promises an acceleration in computing tasks for many applications. We'll come back to this. Then there is the quantum simulator, which manages to simulate much better complex many-body physical systems, and hence give rise to a better understanding of these systems, and as a result to more applications in the sector. Then we have quantum communication, which touches upon the field of cybersecurity and how to connect quantum devices over long distances. And finally, quantum metrology and sensing, which promises better precision for measurements. So there are distinct and very important applications for each one of these pillars, the sector. If we focus more, the more short-term quantum technologies that we do not have to wait for decades, as you mentioned, are probably going to come from the two last sectors, from quantum sensing and metrology, and from quantum communication, where we actually have quantum cryptographic systems and quantum sensors, gravitometers, accelerometers, and these type of devices already on the market. Okay, while we cannot say that we have a quantum computer that can actually perform a meaningful task yet. So the very first applications are going to come from these sectors, and then the next ones that are going to take some time, that we don't quite know yet how much time. It's a bit dangerous to go into projections for quantum computing. We'll touch upon a number of sectors, wherever the very first ones are going to be the sectors where we do optimization problems. We need to deal, because this is a range of problems that can be solved, let's say, that can be addressed with a relatively modest size quantum computing devices on the order of a few hundred qubits, which is the next technological frontier. And then there is like a number of sectors that need to solve optimization problems, from energy to transport to financial, critical infrastructures. All sorts of communication and computing systems need this type of algorithms. So yeah, this is the progression I see in the different applications of quantum technologies.
In 2019, France launched a roadmap in artificial intelligence, and a year ago, the president of the French Republic, Emmanuel Macron, presented a 5-year, 1.8 billion national strategy for quantum technologies to finance research in quantum computing, communications, and sensing. France's quantum plan aims to make the country a key player in quantum technology and the host of the world's first hybrid quantum computer infrastructure starting in 2023. Also, the European Commission, under the European Union's current funding framework program, Horizon 2020, supported and selected 3 big thematic future and emerging technologies flagships: to address grand challenges in emerging science and technology. These three flagship programs launched in 2013 and have a lifespan of around 10 years, and a total budget of around 1 billion euros, half from EU funds and half from member state and industry contributions, focus on quantum research, brain research, and research in applications using graphene. Why are the next 10 years in quantum technology fascinating in Europe?
Not only fascinating, they're crucial as well, I would say. I would call it fascinating. There is no question about it, from a technological, from an application perspective. I expect to see wonderful science, fundamental science, because we're not done yet. I should say that we're not yet in the commercial spectrum. This is a field where you see a direct transfer from fundamental science to application sector nowadays. So we're going to see beautiful science. We're going to see transformative research where these science results are going to be pushed into the actual commercial and application domain much faster than what we're used to. I can see this happening. I can see this transformation happening in particular in my field and more generally in quantum technologies. But it's also going to be crucial because we do expect and do hope that all this research and for the quantum technologies are going to actually bring real results and have an effect in I don't know if I would say everyday life. I wouldn't maybe say everyday life in the 10 next years. I would put it more in 20 years. For the next decade, I would expect to see applications, if not in everyday life, at least in specific sectors, like we discussed previously, with concrete applications where we actually use the quantum advantage for real tasks. So crucial in this sense, because I'm going to be a little bit pessimistic. If it doesn't happen in the next 10 years, then it means that we may need more going back to fundamental science and bringing next more developments. I am optimistic. I really think we will see it happening. But you know, it has happened previously in science, like artificial intelligence, because you mentioned it. There had been a boom a couple of decades ago, and then it went a little bit more silent because more research needed to be done to actually bring it. The people who kept working on it, however, and then it blossomed again. So we cannot completely predict what's going to happen. I see a steady progress and a rapid progress in the field of quantum technology. So I'm pretty optimistic that in the next 10 years we'll see absolutely amazing results, and we'll see if we manage to materialize these expectations. I think we will.
Safety is very important, even using today's internet. In quest of enhancing security against hackers, new generation code makers swing from modern classical to quantum, exploiting the laws of quantum mechanics for future-proof transactions. How could we prevent violation of the protocol security in quantum cryptography?
So yes, as you mentioned, cybersecurity and quantum security are very much intimately linked and intricately linked. So the field of quantum cryptography promises to change completely the landscape around cybersecurity. The idea would be that we can bring a level of security for certain high security applications, obviously where such a level of security is needed, that we would not be able to achieve with any available classical techniques. Okay, what does this mean? Is that it means, I'm not going to go into the technical details here, but the idea would be that we can manage to bring a level of security where an eavesdropper, a malevolent party with even infinite computing power, Infinite computing power and time and computational resources, even with a quantum computer, would not be able to break the security of the communication. And this is something that is not available in the classical world. So this is obviously a level of security in principle that is quite unreachable. But in practice, and this is why I'm always, as a scientist, I always need to say a but at the end of my sentence. But one should be very careful, because practical security, as we have seen in practice, is not exactly the same thing as theoretical and idealized security. So one of the important challenges in this field today is to actually make sure that practical implementations of quantum cryptographic systems actually are in line with theoretical assumptions that we do in our proofs. And then there is a parallel development in the field of classical cryptography, traditional cryptography, where we're developing mathematical algorithms that are expected to be robust against attacks by quantum computers. And by combining these techniques, both mathematical and physical based cryptographic techniques, I think we can bring a very, very high enhanced level of security in all these sectors where cybersecurity is important, a huge number of sectors where cybersecurity is important. I think we don't realize how much impact these developments can have actually in our communications, in a world where everything is happening with huge data rate transfer of secure communications for anything, for any transactions we do. The highest level of protection we can have, the better it is.
Many might think that quantum applications is a new concept. Actually, the first quantum revolution started half a century ago, introducing electronics and photonics. We experience a second quantum revolution in an attempt to control and leverage entanglement and superposition, which will reflect on real products and services, such as next generation computers, encryption, and sensors. Nobody really knows quite how or why entanglement works. It even baffled Einstein, who famously described it as spooky action at a distance, but it's key to the power of quantum computers. In a conventional computer, doubling the number of bits doubles its processing power. But entanglement, the phenomenon when a group of qubits are generated, interact, or share spatial proximity, add extra qubits to a quantum machine, producing an exponential increase in its number crunching ability. What could be the difference between the quantum internet to the existing one?
Yeah, that's a very good question. So yes, exactly as you said, physical properties like superposition or entanglement that are the resource now for a quantum network, for a quantum internet, if you like, means that we have a reshuffling, a huge, complete redesign of our whole network structure from the very, very, very bottom physical layer, which essentially means like as if you change the cables, right, in your classical internet. And the way which actually affects, obviously, immediately the ways that you encode the information that is transferred in the information network. So the goal of any computer information network is to exchange information, right? And then if you go and look at the network science, you will see that there is a whole layer structure where you start from the physical layer. This is the optical system interconnects, I think it's called. And so you start with the physical layer, which is your actual resource that you use for connecting your systems, your information systems, and then goes by packets, by segments, by all sorts of different protocols on how you route information in your network optimally, so that you can go through the millions and billions of users that we have today on the classical internet, up to the applications sector, the application layer, which is almost agnostic with respect to the physical layer, right? So in the very upper layer, you don't even care exactly how the information was transmitted, in what form and in what package and segment, but you care, or transported, but you care about what you want, the task that you want to do. Us as users, this is what we see see when we do a Zoom conference or anything like this, we see just the upper layer. So what the quantum internet comes and does, it changes from the very, very bottom, which essentially means is that you will have to redesign the whole structure of this layer, and there is very active work happening at the international level in this direction, in these quantum internet working groups that are part of research frameworks that are working on internet applications, on how exactly to formalize this, how exactly you are going to route information, how you are going entanglement, how you are going to use this entanglement resource, and optimally and efficiently transport this information on a future quantum internet, so that you can give rise to the applications exactly in the same way that we do in a classical internet. So the way that our community sees this today is we see this as complementary. So we don't expect the quantum internet to come and replace the classical internet. There is probably not going to be a need for a quantum internet, you know, for like a Zoom conference. You never know, huh? You never know. Maybe one day we will get there. But for the moment, what we would like to use the quantum internet for, the quantum internet network for, is specific applications like, for example, connecting quantum computers, right? Or quantum sensors, or securing communications between critical infrastructures. Okay, and for that you will need quantum communication and the whole layer of a quantum internet. So I think again I have this vision of a progressive work towards a quantum internet coming to complement the classical networks we use in our everyday life for well adapted specific applications. That's how I see it.
Quantum information networks are a major goal in the field of quantum communication technologies. The core mechanism of a quantum information networks demonstrated more than 2 decades ago in quantum state teleportation that consumes quantum entanglement and can be considered a new kind of network resource. By what means could quantum information networks improve significantly the quantum device's core processing, sensing, and security capabilities to allow the quantum device's connection over long distances?
Yeah, absolutely. So this touches upon a little bit what we talked about in the previous point. So what you are referring to is one of the most advanced applications that we expect from quantum networks or from the quantum internet, that is called distributed quantum sensing or distributed quantum computing. So the idea would be here that by connecting all these devices, that you actually take advantage of their power in a distributed fashion. So this is something, as we are advancing in technology, these are topics that are being studied more and more. In more and more detail. I wouldn't say because we don't yet have a real, quantum internet or a real quantum computing device. We can't really, for the moment, implement them, do test beds, and what we do is that we anticipate the protocols. So we're developing it, so theoretical work and simulation work. So on the one hand, we need to consider which protocols we needed to actually demonstrate this advantage in this distributed fashion, and then on the second, in the second point of view, is to look at how to simulate it with real devices and see how this will actually look for real networks when they actually come. So we definitely expect an advantage from such advanced applications, and we're looking in this research to quantify it, to actually see and steer research in this direction, so that we can actually take full benefit from such an advantage.
Messages sent over a certain node become entirely vulnerable once the node is compromised and the attacker identifies the keys stored within this node. Quantum technologies have the potential to boost in an unmatched way the security of communications across network infrastructures. The entangled photonic resources are important in design of such infrastructures architecture, as they can help in overcoming the need for trusted nodes. How can the entangled photonic resources alleviate the need for trusted nodes in cryptographic scenarios?
Absolutely. So yes, so this request to think a little bit more deeply about the structure of quantum networks. The description that I was doing just earlier was assuming that we do read that we know how to route entanglement through a quantum network. So what does this mean? If we go in a little bit more technical details, it would mean that you would know how to teleport. Okay, this is how the technical term we need here. So we need to teleport information via entanglement in our network. And when you do this, we know that teleportation can be done, and entanglement routing in this fashion of swapping this type of terms that we use in this field can be done without necessarily trusting the intermediate devices. So this is important because as we said, the goal, one of the most important applications of a quantum network, beyond the capacity, the capability of allowing for applications like distributed quantum computing, is also to do this securely. For example, you would want to, over a long distance, delegate a task to a quantum computer, or via a secure communication channel, or you would want to send secret messages over the network. So if you have and we know, because we're based on the communication of optical systems of photons, in this particular case via quantum channels like optical fibers or satellite links, we know that we're losing our photons. This is a problem. We have inherent losses, we lose them, and so we need somehow a sort of repeater, to propagate this information over long distances. So in classical communications, you will see, for example, in transatlantic links, if you want to go from Europe to the US, you will have several repeaters on the way, amplifiers, that take the classical information, the photons, they amplify the signal and then send it back to the next segment. Okay, so every few hundreds of kilometers, you do this type of thing. So the problem is that quantum communication, we cannot do this. That's why we cannot have this type of series of amplifiers and segments. Why can't we do this? Because we rely on quantum correlations, on quantum properties, and we lose them. And we lose them when we amplify them. We don't know yet how to repeat information without introducing noise. And actually, it's not that we don't know yet, we know it cannot be done. So we need other devices. So the most natural way of doing it is to assume a trusted node, as you say. So basically, what does a trusted node mean is that you perform your communication over the segment, you reveal the information in this intermediate node, so it means that it needs to be trusted, okay? And then you go on and you propagate your information through the network, through these trusted nodes. So the idea would be here that somehow combine or find an equilibrium and balance between trust requirements and practicality, because we don't know yet how to route entanglement with repeaters over very long distances. We know how to do it with trusted nodes. So all the challenge here and the research that is happening in this field is to somehow at least diminish the number, reduce the number of trusted nodes that are required, or keep it in secured locations, or somehow find a good balance between such requirements to make sure that we can bring the benefit of quantum technologies in the short term.
One last question, Eleni, before we finish our thought-provoking and exciting discussion. Why could quantum computing revolutionize the way we do research in STEM today?
Difficult question. So why? So quantum computing is a tool, right? A quantum computer can be seen as an extremely powerful device by itself, but also the product of an unbelievable series, honestly, of an unprecedented series of fundamental science results and engineering. So to be able to do an actual quantum computer, it takes not only physics, engineering, electronics, all sorts of different capacities, computer science, mathematics, all sorts of expertise is brought together to be able to come up with a quantum computer. So from this point of view, it's a subject of research by itself. itself. Okay, so it can actually revolutionize the way that we understand if it can be done, and it will be done. I'm quite sure about it one day. It's a topic that can change by itself, by the fact that it even exists. Understanding of science, and therefore of applications in STEM. So it is already a research topic by itself, and via its applications, it can also revolutionize the way, for example, that we see science, the way that we study many body physics or other topics and application sectors. It will bring and not only is it a topic of research by itself, but it will bring opportunities and capabilities that will open new avenues in research in STEM. This is how it's in many sectors.
Very exciting years ahead. Thank you, Eleni, for accepting the invitation of the Global Greek Influence podcast and being here today.
Thank you very much. You're very welcome. It was a pleasure.
Thank you all for staying until the end. Please remember that if you don't want to miss another live streaming on YouTube, subscribe to the YouTube channel Yota Pimenidou and the podcast platforms for a new episode every 2 Sundays. Until next time.